You think you know Saturn, the beautiful planet with the spectacular rings. The one that looks almost like a toy through a telescope. But there is something you need to understand. Saturn is not simply beautiful. It is one of the most extreme and mysterious worlds in our solar system. For decades, scientists studied Saturn with increasingly powerful telescopes and spacecraft. Then the James Webb Space Telescope looked at the planet in infrared wavelengths and revealed details that were almost impossible to see before. And some of those observations are forcing scientists to rethink what happens inside Saturn's upper atmosphere. Let us start with the scale of this world. Saturn is the second largest planet in the solar system after Jupiter. Its diameter is about 9.5 times that of Earth, and its volume is large enough to contain roughly 760 Earths. Its atmosphere is also incredibly violent. Near Saturn's equator, winds can reach more than 1,000 kilometers per hour. That is several times faster than the strongest winds produced by the most powerful hurricanes on Earth. And then there is Saturn's North Pole. This is where one of the most recognizable structures in the solar system appears. A gigantic six-sided atmospheric pattern known as Saturn's hexagon. It was first observed by Voyager spacecraft during their flybys in the early 1980s, and it has remained visible for decades. The structure stretches roughly 30,000 kilometers across, making it several times wider than Earth. Inside the hexagon, enormous atmospheric currents race around Saturn's North Pole. Scientists believe the basic structure is produced by an unusual interaction between Saturn's high-speed jet streams and the fluid dynamics of its atmosphere. But knowing how the hexagon forms does not make it any less extraordinary. A six-sided atmospheric pattern has persisted on a gas giant for decades. And until recently, scientists could see only part of the story. They could observe the clouds and winds relatively deep in Saturn's atmosphere. But what was happening hundreds of kilometers above those clouds was much harder to study. That changed when Webb observed Saturn in infrared wavelengths. Infrared observations are especially useful because they can reveal temperature differences, chemical emissions, and structures hidden from ordinary visible light cameras. Webb's instruments detected emissions from molecules including H3+, a positively charged form of molecular hydrogen that is an important tracer of Saturn's upper atmosphere and auroral activity. These observations gave researchers a new view of Saturn's ionosphere and thermosphere. And the results revealed just how complicated the planet's atmosphere really is. Saturn's auroras are created when charged particles interact with the planet's powerful magnetic field and upper atmosphere. The resulting energy can heat the surrounding atmosphere and drive complex circulation patterns. Those processes can affect the temperature, chemistry, and electrical behavior of the upper atmosphere. In other words, Saturn's famous storms are not isolated weather systems. The planet's atmosphere behaves more like an enormous interconnected machine. Changes in one layer can influence another. And the magnetic field adds another layer of complexity. This is also connected to one of Saturn's longest-running mysteries. For decades, scientists struggled to determine Saturn's exact rotation period. That sounds strange. A planet spins. You measure how long one rotation takes. But Saturn does not have a solid surface. There are no mountains or continents that can be tracked from one observation to another. Instead, scientists relied partly on radio emissions and magnetic field-related signals associated with Saturn's interior and auroral environment. Different spacecraft produced measurements that did not always agree. The apparent rotation period seemed to vary by several minutes. That created a serious puzzle. Saturn itself was not necessarily changing its spin. The problem was that the signals being used as a clock were influenced by Saturn's complex atmosphere and magnetosphere. Researchers eventually showed that atmospheric processes and auroral activity can affect the signals used to infer Saturn's rotation. In other words, the clock was not broken. Scientists were measuring the wrong thing. That is an important lesson in planetary science. Sometimes the mystery is not that nature is violating the laws of physics. The mystery is that we have been observing one part of a much larger system. And Webb is allowing scientists to see more of that system than ever before. The upper atmosphere is particularly fascinating. Saturn's aurora can produce powerful heating. That heating can drive atmospheric winds. Those winds interact with the ionosphere and generate electrical currents. Those currents are connected to Saturn's magnetic environment and auroral emissions. The result is a complicated feedback system involving the atmosphere, magnetosphere, and aurora. It is not a simple weather pattern. It is a planetary-scale interaction between gas, electricity, heat, and magnetic fields. And then we have Saturn's rings. From Earth, they look like a smooth, elegant structure surrounding the planet. Up close, they are anything but simple. The rings are primarily made of water ice, mixed with smaller amounts of rocky and dusty material. Their particles range from tiny grains to much larger pieces. The rings also contain gaps, waves, spirals, density variations, and other structures created partly by the gravitational influence of Saturn's moons. They are an enormous dynamical system. And one of the strangest things about them is their proportions. The main rings extend hundreds of thousands of kilometers across, yet in many places they are astonishingly thin compared with their enormous width. They are more like an immense cosmic sheet than a solid disk. Infrared observations also reveal Saturn very differently from visible light images. Different wavelengths allow scientists to investigate different layers of the atmosphere and different properties of the ring particles. When Webb and Hubble observe Saturn together at different wavelengths, researchers can compare atmospheric structures that appear at different altitudes. That helps create something close to a three-dimensional picture of Saturn's atmosphere. And what emerges is a planet with layers upon layers of complex chemistry, temperatures, winds, clouds, hazes, and electrical activity. Saturn is not one simple atmosphere. It is a collection of interconnected environments. And then there are the moons. Saturn has an extraordinary moon system, containing dozens of confirmed satellites with a huge variety of sizes and compositions. Some are tiny irregular objects. Others are worlds that could completely change our understanding of where life might exist. Take Titan. Titan is Saturn's largest moon and is even larger than Mercury. It has a thick nitrogen-rich atmosphere and an active weather cycle. But Titan's rivers, lakes, and seas are not filled with liquid water. They contain liquid methane and ethane. Clouds form. Rain falls. Rivers flow. Lakes collect the liquid. Then it evaporates and returns to the atmosphere. It is a strange version of Earth's water cycle, operating with hydrocarbons instead of water. And beneath all that orange haze is an environment rich in organic chemistry. Titan is one of the most fascinating places in the solar system for studying the chemistry that could lead toward life. Then there is Enceladus. This tiny icy moon may be even more astonishing. Beneath its frozen surface is a global ocean of liquid water. Saturn's gravitational forces flex the moon as it travels through its orbit, generating internal heat. Near the South Pole, cracks in the ice allow material from the subsurface environment to escape into space. Cassini flew through these plumes and detected water vapor, ice particles, salts, carbon dioxide, hydrogen, and organic compounds. That means Enceladus contains several of the fundamental ingredients associated with environments where life could potentially exist. Scientists still do not know whether life is actually present there. But Enceladus remains one of the strongest candidates in our solar system for future astrobiological exploration. And this is what makes Saturn so remarkable. The planet itself is extreme. Its atmosphere contains enormous storms and powerful winds. Its north pole contains a gigantic geometric jet stream pattern. Its magnetic environment produces spectacular auroras. Its rings form one of the most complex planetary disk systems we have ever observed. And its moons include Titan and Enceladus, two worlds that could teach us extraordinary things about planetary chemistry and the possibility of life. We have been studying Saturn for centuries. Galileo first observed it through a telescope more than 400 years ago. The Voyager spacecraft later transformed our understanding of the planet and its rings.